We're now going to discuss coupling in NMR. We're going to use hydrogen NMR as an example because although it's present in all forms of NMR, coupling is easy to explain in hydrogen. There's a tendency for bonding electrons to pair their spin states with the nearest proton. Those electrons will in turn influence the next bonding electron. Although the effect is not really important beyond 3 bonds unless there's electron delocalization, ring strain or a bridge. The splitting pattern of peaks that can be seen in coupled NMR spectra follows the n+1 rule, which is that the number of peaks, number of splits the peak of a nuclei displays is the number of neighbouring coupled nuclei plus 1. So if a nuclei is next to no coupled nuclei, n equals 0, therefore you'll see n+1 peaks, 0 + 1 is a single peak. Each peak has its own name, so for n equals 0, it's a single peak, one lone peak. For n equals 1, it's a doublet peak, 2 peaks. N equals 2, triple peak. N equals 3, quadruplets, so on, up to as high as you would like to go. I suppose it's possible. The line separation between the splits of a peak is always constant for a given multiplet and is called the coupling constant, J. If the chemical shift difference in Hertz for 2 different environments is much larger than the coupling constant, then the normal splitting patterns are observed, i.e. in proton NMR spectrum of the molecule given in the handout. 2 doublets are quite clearly seen. As delta V over J becomes smaller, so as the difference in the energies becomes smaller, the 2 inner peaks begin to increase in intensity and the outer peaks decrease in intensity. If the nuclei is spin coupled to 2 or more sets of neighbouring nuclei with different J values, then the n+1 rule does not accurately describe the splitting pattern. Instead, the splitting pattern of one set of J is added to that expected from the other sets of J, much like the example given in the handout. So for no coupled hydrogens, obviously it's just a singlet. When there is just one coupled hydrogen, HA, there is 2 peaks, gives a doublet with a splitting constant of JA. When there are 2 coupled hydrogens, however, you go down into a double doublet. So it's a doublet split by a doublet, which is 4 peaks of even intensity. Again, as you move up to 3 coupled hydrogens, so H, A, B and C coupled to the hydrogen being observed, you get a doublet, so 8 peaks split evenly by JA value of an even intensity. In aromatic systems, the difference between frequently and coupling constants of a nuclei are so small that normal splitting patterns, like in the example in the handout, are not seen. The only example in the handout, HB is split by HA into a doublet, but is also split by HC as a doublet. The resulting peak is a double doublet, which consists of 4 equal intensity peaks. The magnitude of some typical coupling constants are given in the handout in a couple of tables there. Just look through them. It's good to memorise the ranges, but it's not vital. The spin coupling interactions described in those tables may occur between similar or dissimilar nuclei. For example, a fluorine-19 atom may be spin coupled to a hydrogen atom. Both nuclei in their relative spectra will appear as doublets having the same J constant. Spin coupling with nuclei having a spin other than a spin a half is a lot more advanced and will be covered here. The relative intensities of peaks are predicted using Pascal's triangle. So for a singlet, obviously there is just, like given in the handout, there is just 1 peak of intensity 1 relatively. A doublet is split into 2 peaks, intensity 1 to 1. When you have a triplet, it's obviously 3 peaks split in intensity 1 to 2 to 1, and this is due to the fact that as the doublet is split, you form two outer peaks, but the two inner peaks from that doublet combine to form a peak of the double intensity. As for reference compounds in NMR, tetramethylsilane is usually used as a reference compound in both hydrogen NMR and carbon-13 NMR, as all protons and all carbons are in the same environment, so there is one strong peak observed for each, for the molecule in each spectrum.